Okay then. Good evening, everyone. My name is Rohan, and let's begin the third session for the polymer reaction engineering. So this is the interactive live session, and I will be discussing a few problems which will be helpful for you to solve your assignments for the polymer reaction engineering course. So let's start with a few questions. I guess this week you must have learned about the basics of the reaction engineering and about the polymer processes. So this interactive session will be about that. So let's go through the questions. The first question which we have is which of the following is or are correct? We have been given four definitions here. First, we have the Biot numbers definition, then Brinkman number, Dam-Kohler number, and the capillary number. Here I have given the definitions for each of these numbers, and we can go through them and learn about them, and then we can choose which one of these is the correct answer. So first one we have is Biot number is equal to convection from surface divided by the conduction through the body. So the definition for the Biot number which has been given is conductive resistance inside the solid was divided by the convective resistance in the thermal boundary. Ratio of internal thermal resistance to a solid to the boundary layer thermal resistance. So to explain this, you can imagine in such a way that a sphere having imagine a solid sphere which has been dipped into a tank of water. It has a high temperature. The sphere has high temperature and it is continuously losing heat to the surrounding water. So what's going to happen is the heat from the center of the sphere will first have to conduct and travel through the radius of the entire sphere, and then it will leave the surface of the sphere to the water. So there the convection process will occur, and inside the body you will have the conduction. So the definition says conductive resistance inside the solid. So when you say conductive resistance inside the solid, that basically means the reciprocal of the conduction. So what happens is uh, you can see the definition which has been given here. It's we have the conduction through the body on the bottom part. So conductive resistance inside the solid and conduction through the body will basically come in the denominator. And then when we have the convective resistance in the thermal boundary layer. Now, where is the boundary layer being formed? It is being formed at the outermost layer, where the sphere is losing the heat to the water. Okay, so all the heat which is being accumulated on top on the surface is slowly going away through convection to the water. So that will be on the numerator side. So the first one, according to this definition, is correct. So Biot number is equal to convection from surface mm, divided by the conduction through the body. Next, we have the Brinkman number, which has been given as viscous heating divided by the conduction. So we have the definition for Brinkman number, that is nu u square divided by k Tw minus Tzu. So it is the ratio between the heat produced by viscous dissipation and heat transported by the molecular conduction. The ratio of viscous heat generation to external heating. And exactly that is the definition, and that has been given in the option itself. So you can tell that it's the correct answer. Brinkman number is used for uh, basically in the polymer reaction engineering to see how much viscous dissipation, how much heating is being produced by viscous dissipation, because polymers are extremely viscous liquids or fluids, you can call them. And once in the molten state, or in the native state itself, when they are uh, subjected to different kinds of viscous stresses, you can see that they dissipate that through extreme heat. And that can be given by the Brinkman number. We can see the dominating part of either the viscous heating or the conduction part. Uh, I hope the screen is visible. Like, uh, And I think the audio is also coming through fine. So I will carry on. Next definition which we have right here is the dam Kohler number. So in dam Kohler number, we have the definition has been given as reaction energy by the internal energy. Now we have the definition right here. dA is equal to KL square by D, where the L is the characteristic length, K is the rate constant, and D is the diffusivity. So the characteristic length is the length over which your entire process which you are trying to model is happening. And then we have the rate constant K that will be for your reaction rates. And then we have the diffusivity meter square per second. So the definition which has been given here is the reaction energy for the internal energy. So Damkohler number is basically used to find the ratios or to compare the transport scale properties with respect or the transport scale properties and the chemical reaction properties. So what's happening in that case is the ratio which has been given right here, KL square by D. The K part specifies the reaction rate and which can be synonymous to the reaction energy which has been given in the option right there, divided by the internal energy, and which is synonymous to diffusivity. Why? Because diffusion is happening because of the chemical potential, or you can call it that the diffusion in itself is happening because of the concentration difference, and that can be synonymous to the internal energy of the system or the particular particles. So, so that through that definition, you can tell that the dam Kohler number is equal to the reaction energy by the internal energy. So it has been given right here. Next, we have the capillary number, which is defined as the surface tension stresses divided by the deviation stresses. Now, the definition here says that it's the ratio of the viscous force to the surface tension. So it is not according to the definition which has been given right here. Capillary number is usually used for interfaces where there are maybe invisible liquids or sometimes the action of one liquid over the other. So in that case, you define the capillary number. And you can see right here that the ratio of viscous force to the surface tension force is the definition, but it's not matching the given option. So the first three are correct, and the fourth one is incorrect. Answer for this question. And next one we have true or false type question. So the normal stresses in the fluid originate from the tendency of the polymer molecules to curl up while they are stretched in shear flow. So what's happening is when you are stretching a polymer in shear flow, that is like the usual forces which are being applied during the shear process. What happens is the polymer molecules which are coiled up together stretch, but they want to return back to their original position. So because of that, what happens is these chains which you can see right here, they start opposing the shear flow direction, and then they start giving out the normal stresses to their plane, normal to their plane, which in which they are oriented. Based on that, they are generating the normal stresses inside the fluid body entirely, the polymer fluid, and then you have the normal stresses generated. So this option is true. Next, we have another number definition. That is, what is the Becklet number used to characterize in fluid dynamics? So for fluid dynamics, we have the Becklet number involved here, and we have four options. That is the ratio of inertial forces to viscous forces, the ratio of gravitational forces to buoyant forces, the ratio of heat conduction to heat advection. So in this case, the inertial forces to viscous forces is clearly you can tell by the definition itself that it's Reynolds number. And gravitational forces to the buoyant forces can be given by the Grashof number. And next we have the ratio of heat conduction to heat advection. This ratio is what is defined by the Becklet number. So the heat conduction to advection ratio is what is called the Becklet number. Usually, it, the use of Becklet number in reaction kinetics is reaction chemical reaction engineering is that Becklet number is used as a metric for the dispersion of the medium inside a reactor. So with respect to that, you define the Becklet number. So the rate of advection for physical quantity by the flow, the rate of diffusion to the same quantity in the approximate gradient is what you can define as Becklet number. And its definition can be given as the heat conduction to the heat advection. And moving on to the next question. Which of the following statements is true about the thixotropic fluids? First one is their viscosity decreases with increasing shear rate. Then we have they exhibit a constant viscosity regardless of the shear rate. Their viscosity increases with the increasing shear rate, and they do not exhibit time-dependent changes in viscosity. So, according to the definition of non-Newtonian Newtonian fluids, we have several kinds of fluids. Most popularly, you might have known about the Bingham plastic, pseudoplastic, and then we have the dilatant fluids also. So these fluids do not show any kind of time-dependent properties. They are quite straightforward in their behavior, as in the Bingham plastic requires a threshold shear stress, after which it starts moving. And then the dilatant fluids, where as you keep applying the shear stress, their viscosity increases. Or you can say that the slower the shear stress which is being acting upon it, the better it flows. And the higher the shear stress, the slower it flows because of the certain particles which are present inside the shear fluids, the dilating fluids. So where does thixotropy fit in? So thixotropy and rheopectic fluids are the two fluids which show the time-dependent properties. Thixotropic, in this case, decreases the viscosity of this fluid decreases with increasing shear. So if you keep, and that happens with respect to time. So as you keep increasing the shear rate, their viscosity will keep decreasing as time goes. And that is a time-dependent behavior shown by thixotropic fluid. Whereas rheopectic fluid, the viscosity increases with increasing shear rate. As you keep increasing the shear rate, the viscosity will also keep increasing. So the correct answer for this question is the first one. The viscosity decreases with increasing shear. Next one we have for polydispersity index, which statement is correct? We have four options here. It is the ratio of weight average molecular weight to the number average molecular weight. It is usually 1 for monodispersed polymer or greater than 1 for actual polymer. It is used as a measure for the broadness of molecular weight distribution. And the last one is the polymer with the number average molecular weight alone with considering the polydispersity may mislead. So which of these statements is correct? We need to find out. So first of all, the definition of polydispersity index from the first class, we know that it's the weight average molecular weight of a polymer divided by the number average molecular weight of a polymer. I hope I'm audible because you can write in the chat box itself if like if I'm having like if you are having any issues on your end, so you can just tell me. Okay. Then this is for the polydispersity index. So first one is the ratio of weight average molecular weight to the number average molecular. That is the classical definition for the polydispersity index. And what does polydispersity index define? Uh, let's draw the polydispersity index right here, like a sample of how it should look like. So the polymer dispersity index will be looking something like this. So on the x-axis, you will have the molecular weight, which is increasing, and on the y-axis, you will have the fraction. You can call it ni or something, kind of variable, which tells you the fraction. Okay. So what's happening is that the broadness of the scale, you can see this curve right here, but the broadness with which this curve is present right here is what defines the polydispersity index. And why is it called, uh, why is it a ratio? I will tell you. So when you're defining the number average molecular weight, let's position it right here. So the first stick is the number average molecular weight. The second stick I will position right here will be the weight average molecular weight. As we already know that weight average molecular weight is higher than the number average molecular weight. Why does that happen? It happens because the weight average molecular weight considers the weight of the highest chain while accounting for the average molecular weight. Whereas the number average molecular weight accounts for the highest number of a particular size chain, which is present inside the polymer. So the average is based on that. So that's why weight average molecular weight will always be higher than the number average molecular weight. So the first line represents the number average, and the second line represents the weight average. So you can see right here that the distance between these two lines and the curve around it, if the ratio of these two is known, you can particularly find out the FWHM, or the full width at half maximum. That is basically the broadness of this curve. Okay. So the broadness of this curve is defined in that way. And then the second option is it is usually 1 for the monodisperse polymer or greater than 1 for actual polymer. Now, no polymerization technique is 100%, what should I say, efficient, which means that there will always be a discrepancy in the molecular dynamics of the chain itself. So what happens in that is that not all chains will have the same length, and the distribution might be really broad or sometimes very narrow. But it cannot be like a single line. And when does a single line happen? It will happen when the polymer is monodisperse. And when does that happen is when the weight average and the number average are equal. If these two lines were to be merged, let's say they're merged like this, the entire distribution, what will happen to the distribution? It will shrink down. It will basically shrink down to a single line like this. And that is what is for a monodisperse polymer. But that is not the case in actuality. For actual polymers, it will always be a distribution like this. Okay, so we will have a distribution like this always. So the second option is also true for the definition of the polydispersity index. Third one is it is used as a measure of the broadness of molecular weight distribution. Correct. As I have been explaining, you can use it as a broadness factor for the molecular weight distribution. Fourth one is a polymer with the number average molecular weight alone with considering polydispersity may mislead. So if you only consider the number average molecular weight alone with considering the polydispersity index, it may mislead. Why? Because first of all, you are not considering the other half of the polydispersity index, so you only have that number average molecular weight. So if you were to make your calculations based on just that, that might cause you trouble. So what you do is you calculate the weight average by putting it into the ratio of weight average by number average and multiplying the number average with the polydispersity index, which will give you the weight average, and you might have the entire idea about the molecular weight distribution. Moving on to the next question. So, what are other classifications of suspension polymerization? So we have these suspension polymerization right here. Uh, so, what are the classifications of suspension polymer? First of all, we need to know what is suspension polymerization. As the word itself suggests, suspension and polymerization process. So, what do we understand by that is that in this process, uh, the polymerization of the monomers occurs and it forms a suspension in the dispersion medium. So, mechanical agitation or any kind of impelling force is used to mix the monomers, usually in the liquid phase where they are suspended and you are reacting them. The liquid phase is used basically to increase the handleability of the polymer since it becomes extremely viscous once it is polymerized. And the temperature increase during polymerization is also very prominent. And to control that, also, you can use the liquid. So you have the liquid phase and you are polymerizing in that. And once the polymer is formed, it forms a suspension. Now, how can there be classifications for such a polymerization reaction? First of all, suspension polymerization is a radical kind of polymerization, radical polymerization. And in that, what happens is if the polymer which is forming is soluble in your monomer, which means that if there is some leftover monomer and if the new polymer which has formed is soluble in that monomer, what will happen is it will form a bead. It will form a bead-like structure. You can see right here that bead-like structures will form where the polymer will solubilize and reform a coagulated small section where it will look like a bead. And this bead formation is why the term bead polymerization comes into picture. And if the polymer is not soluble in its monomer, it will be present as a it will be present in small separated molecules, and that gives it like a powder-like appearance, and that's why it's called a powder polymerization. Emulsion polymerization is a altogether different kind of polymerization process where the polymer is emulsified using a surfactant. So with suspension polymerization, we do not have any kind of surfactant. So that's why the classification will only include the two, bead polymerization and the powder polymerization. So these two are the classification of the suspension polymer. Next, we have which one of the following properties of the polymer is desirable during the synthesis of the polymer. So what are the properties which you are aiming for when you are trying to synthesize a polymer? So usually whenever we are trying to synthesize a polymer, its application is basically uh, polymers are basically used as a replacement for many materials. So it has to withstand certain mechanical property. It has to withstand certain mechanical testing, which means that we need good properties in polymers. And good properties can come from the control on the molecular weight. So the higher the molecular weight, you will have better mechanical properties of a polymer. So that's why low molecular weight is an undesirable property in polymer. Like it's for like I would say that majority of the applications would require a molecular weight of a certain range, and we would not want a lower molecular weight because lower molecular weight would make the polymer in itself fragile. But if that is the need of your application, it can be one of them. So it's quite a subjective term, but in the majority sense, you can tell that the lower molecular weight is undesirable. Next, we have the impurities. So what happens in the impurities is that we do not want impurities. So that is again undesirable in the sense like uh, while polymerization reaction, we do not want any impurities because that might create the defect in polymer or it can hinder the polymerization process altogether. So that in itself will create problem. So what happens next is uh, that because of this impurity, your final finished product will have some imperfection. So that final product will have some imperfection. So that's why you would not want impurities. It's undesirable. Now the third one is low viscosity. Now, why lower viscosity would be desirable? One of the reasons why lower viscosities can be desirable is because the handling of the polymer becomes very easy because Viscous polymers can create a lot of problems. First of all, in various machines and the processing of the polymer in itself is what makes it uh, such a challenge because the processing temperature of a polymer is often higher than the it's basically higher than the melting point. Why is why is that done? Because even at the melting point, the polymer is not handleable. You cannot process it properly using the machinery that we have. So that's why you have to take the temperature even farther ahead. And because of that, the viscosity is low enough that the polymer becomes handleable and you can handle it properly. That's why low viscosity is desirable. Uh, that is one of the qualities of a polymer which will be looked for. Like it should have high molecular weight but low viscosity. It sounds very counterintuitive, but that's not the case. Uh, Low viscosity is desirable for increasing the handleability of the polymer. So moving on to the next question. Completely amorphous polymers show Tg, glass transition temperature, and crystalline polymers show Tm, melting temperature, and semi-crystalline polymers exhibit both temperatures. So first of all, first definition is that all polymers are semi-crystalline in nature. The only distinction between the amorphous and the crystalline polymers happens because the semi-crystallinity is distributed over a range, as in that some polymer will have 80% crystalline structure, 20% non-amorphous, or it might have 80% amorphous and 20% crystalline. But uh, the major definition is that all polymers are semi-crystalline in nature, and they will show they will show uh, they will show different properties such as the crystallinity and amorphous nature based on the percentage of either properties present inside that. So firstly, we have the amorphous polymers. What happens in amorphous polymers is that all chains are already disorganized in different forms. So they do not have a particular packing factor involved where the chains are packed together properly. So the chains are already disorganized. And why is it showing a glass transition temperature is because even if the chains are disorganized, there is a particular temperature over which they will start moving around or they will become free enough to overcome the secondary forces which are involved between the chains. So that's why even the amorphous polymers will show you the glass transition temperature. Next, we have the crystalline polymers. Now, what happens to crystalline polymers is that since the crystalline nature of the polymer is much higher than its amorphous one, the polymer chains are arranged in proper spherulites and the lamella structures. Now, what are spherulites and lamella? Lamella are the structures which are it's a zigzag structure which is quite ordered and it is formed because the polymer chains and the secondary forces are actively arranging them into a certain close packing structure. And because of this, individual lamellas will form spherulites. Okay. So when you have extremely high crystalline polymer, as you increase the temperature, the packing factor and the secondary forces are strong enough that the polymer does not react that much to the increasing temperature and it directly melts. That it will reach a threshold temperature where the chains suddenly have enough energy to move around, and because of that, your polymer will start moving around. Basically, it's molten. And that's the exact reason why crystalline polymers will show a good melting temperature and amorphous polymers show a small glass transition temperature also. Okay, so you can see this diagram right here that shows how if the temperature increases, how your stiffness modulus of the polymer will change. So if you have an extremely crystalline polymer, definitely its modulus will be high. So in the initial stage, it's a glassy stage. And as the temperature increases, it goes on to the glass transition temperature, where the properties of the polymer start changing. And as you keep uh, increasing the temperature, it will reach to a rubbery state where the polymer becomes extremely flexible. It has no rigidity inside it, and then it will start rubbery flow, and at the end, it's molten and it becomes viscous. So it is a viscous fluid. On the right hand side, we have a DSC scan, that is the differential scanning calorimetry scan, which is showing the heat flow versus temperature. And you can see right here the glass transition, crystallization, and the melting effects right here. Okay. So the first small dip is the glass transition temperature, where you can see that the polymer inside the heat flow is occurring inside the polymer. And as the temperature proceeds, then we see the crystallization peak, and then we have the melting. Okay. So the heat flow inside the DSC can be up or down in the sense like the curves which are shown of a DSC scan. It can be either on the basis of an endothermic process or an exothermic process. So based on that, the direction of these peaks can change. Okay, so that is for some, like, if you are into research and you're working with different polymers, you might know it better than what I'm explaining right now. But exactly that's what it is. And the answer for this question is true, that completely amorphous polymers show only TG, and the crystalline polymers show TM, and semi-crystalline show both of them. Then we have choose the correct option from the following statements. In the Arrhenius law, the reaction rate constant is directly proportional to the temperature. In the collision theory, the reaction rate constant is directly proportional to the square root of the temperature term. In the transition state theory, the reaction rate constant is directly proportional to temperature term, and the collision theory is based on the kinetic theory of gases. So first of all, we have in the Arrhenius law, the reaction rate constant is directly proportional to the temperature. So we know how does the uh, Arrhenius equation looks like. Okay, where you already know the definition of it, that the uh, rate constant is not exactly proportional to temperature. As the temperature slightly increases, the rate constant is doubled, and it increases exponentially over time with respect to that. Okay, so first statement is definitely not true. Then we have in collision theory, the reaction rate constant is directly proportional to the square root of the temperature time. If you have already gone through source notes and attended the lectures, you'll be able to answer this one. And this is clear that the collision theory, the reaction rate constant is directly proportional to the square root of the temperature. In the transition state theory, the reaction rate constant is directly proportional to the temperature term. So in transition state theory, what happens is that we are seeing the change. We are seeing the change with respect to the temperature. The reaction rate constants are uh, like as the temperature is increasing, the reaction rate also steadily rises with that rate. And then the collision theory is based on the kinetic theory of gases. This is also true because the collision theory, that the molecules need to collide together to cause reactions, is basically coming from the kinetic theory of gases. And we already know what are the basic principles, basic postulates of the kinetic theory of gases, and how it has been established already. So these three are the correct options. Next question. We have which of the following statement is in incorrect for the order of the reactions. Now, what was the definition for the order of the reactions? It is the sum of the stoichiometric coefficients to which the reaction concentration terms are raised. So the overall order of the reaction can be a fraction or a whole number. So yes, that is true. It can be a whole number and sometimes it can be fractional. Depends on how the reaction is proceeding and to what the stoichiometry of the reaction is defined. The sum of the power raised to the concentration terms in rate law is said to be the order of reaction. That is true. So these two statements are true and are not incorrect. And the third one is it can be defined for the elementary and non-elementary reaction systems. So the definition for that, it can be defined for elementary and non-elementary systems. Non-elementary reaction systems are basically a series of elementary reaction systems to complete a single reaction. So yes, order of reactions can be defined for both elementary and non-elementary. This is also true. And the last one is the order of reaction and molecularity are always same for a reaction. Now, this is not true. Why? Because order of the reaction is basically the related to the stoichiometry of the reaction environment. Whereas the molecularity is the amount of molecules which are participating in the reaction in itself. These two numbers can vary sometimes. So that is the exact reason because it's quite difficult to tell what is the molecularity involved in that particular reaction. And sometimes the molecularity is not equal since the exact for the exact reaction to happen, the number of molecules which are involved might be different than that. And that is the exact reason why the order of reaction and molecularity are not always the same. So the fourth one is the incorrect option for that. So I hope that you might have understood today's class. And if you have any doubts, you can ask me. If you have any problems in your assignment solving or any doubts regarding the class or something, you can ask me. I'll try my best to clear them. If you guys have any question, you can ask me, or else the class is over. So you can, if you want, you can leave if you don't have any doubts. Hello, Mohammed. We'll start explaining the questions to you right now. Okay, so starting from the first question, which of the following is or are correct? We have been given here four dimensionless numbers, and we are asked which definition is correct. So I have put the definition of all four here, and which will make it quite easier for us to understand each number and its role. So the first one we have is the Biot number, where we have been given that Biot number is equal to the conductive resistance in solid divided by the convective resistance in thermal boundary layer. So this can be understood by thinking that whenever the heat has to travel from inside a solid body to its surface, and then from the surface it will be liberated outside by the convective transfer. So what's happening here is we have the convection from the surface divided by the conduction through the body. So that is the definition right here. So you can understand this uh, from the definition which has been given conductive resistance in solid. So when it is saying the resistance in solid, which basically means that the reciprocal of the conduction. So basically resistance is the reciprocal of conduction and vice versa. So you can understand it by seeing that the conduction term is in the denominator right here. And then we have convective resistance in thermal boundary layer that is on the top. That is the convection from the surface. So Biot numbers definition is correct. Next we have the Brinkman number. So what's happening in Brinkman number is that we have the ratio between the heat produced by the viscous dissipation and the heat transported by the molecular conduction. So how can that be understood? Uh, we can see right here in the definition it's saying that the viscous heating divided by the conduction. And the Brinkman numbers definition right here is saying the viscous dissipation mu multiplied by u squared divided by ETW minus T, which can be seen right here. So this is basically useful for the polymer reaction engineering because polymers are quite viscous and any shear, any kind of shear forces or any kind of forces acting on the polymer heat them up because they are viscous and their any movement in their body or anything will create heat dissipation. So the viscous heating is shown right here. Viscous heating divided by the conduction, conductive heat transfer. Next we have the Dam Coulomb number. The definition for which is given right here. Uh, the definition in the option is shown as reaction energy by the internal energy. And then option which we have right here is the KL square divided by D. So what does this mean? Is that we have the definition that first on the numerator we have the K, that is the rate constant, which is exactly associated with the reaction energy. And in the denominator we have the diffusivity. Now, mass diffusivity, you can think of it as the diffusion is occurring because of the potential which is present between uh, potential which is present because of the concentration difference or the energy of the molecule in itself. So the reaction energy divided by internal energy is definition is correct. Then last one we have the capillary number. Now, for capillary number, we have the definition as surface tension stresses divided by the deviation stresses. And the definition which has been given right here is the ratio of viscous force to the surface tension force. That is the mu by sigma. Now, the definition does not match that, and the capillary number is basically used for immiscible liquids or any kind of uh, places where there is an interface form, since there is the capillary effect observed. So that's why the ratio of viscous force to surface tension is the correct answer for this, and the surface tension by deviation stresses is not the correct definition. So you can see right here. Next, we have the true false state question, where it has been asked normal stresses in the fluid originate from the tendency of the polymer molecules to curl up while they are stretched in shear flow. Now, we have a polymer molecules diagram right here, and it's just a molecule diagram. And you can see that how the monomers are present and how the polymer chains are coiled up. Now, the tendency of the polymer chains is to stay coiled up as it is. If you subject them to any kind of shear flow, what they will do is they will try to resist, and that resistance will give them the tendency to curl up again. And because of this curling up, what will happen is they will start giving out the normal stresses to the direction of the polymer, in the direction of the polymer chains, normal to that direction. And that will result in your normal stresses being generated. So this is true. Next, we have what is Pecklet number used to characterize a fluid dynamics. So from the general definition of Pecklet number, we can see that it is the ratio of heat conduction to heat advection. And where does the Pecklet number play a role? It is very useful in the dispersion models for the reaction engineering, where Pecklet number is used as a decisive measure to see the if the dispersion model is working correctly or not. And that's exactly how the Pecklet number is defined as the heat conduction to heat advection ratio. Next, we have which of the following statements is true about thixotropic fluid. Now, you already know the definitions for the different Newtonian and non-Newtonian fluids. Non-Newtonian will consist of the Bingham plastics, the dilated fluids, and the pseudoplastics. So, how does thixotropic and the rheotropic and the rheopectic fluids come into picture? So, these two fluids are special because they have time-dependent properties. Time-dependent properties in the sense like what happens is as the shear rate is increased with respect to time, as the rate is increasing for the shear, the viscosity decreases, which means that the fluid is thinning out. So basically, that is exactly what is a thixotropic fluid. Whereas a rheopectic fluid, its viscosity will increase with the increase in shear rate. So that is a rheopectic fluid.
Excuse me, sir. Can I ask a question?
Yeah.
Actually, thixotropic is actually conveyed on the Bingham fluid now. Thixotropic and rheopectic are around the Bingham fluid.
Not exactly on the Bingham fluid. Yeah, they will show time dependent behavior. So they are kind of conveyed to that.
Okay, so they are subsequent towards Bingham fluids.
Hmm, kind of. You can say that. They are synonymous to that. Yeah,
Oh,
yeah. You can say it. I think you might have already understood this. So thixotropic fluids are viscosity which decreases with the increase in shear. Next, we have what is for polydispersity index, which statement is or are correct. So we have been given four options. If you would have already attended the first class, you might have witnessed this question already. And we can see right here that first option is it is the ratio of the weight average molecular weight to the number average molecular weight, which is the classic definition of the polydispersity index in itself. So that is true. And then we have the it is usually one for monodispersed polymers or greater than one for the actual polymer. Now that is again true since the actual polymers in the polymerization process cannot produce all equal length chain polymers. So that's why monodispersity is very difficult to achieve, and it is always greater than one for the actual polymers seen in the real time. Then that statement is correct. Third one we have is it is used as a measure of the broadness of the molecular weight distribution. Now you can see right here that we have the distribution of the molecular weight distribution, and we know that number weight average is always higher than number average. So you can see the first line being number average and the second line being weight average. So we can see that weight average is higher than number average, and through that comparison, you can tell that the distance between them can roughly give you an estimate of how the broadness of this entire distribution will be. So, third option is correct. Then fourth one is the polymer with the number average molecular weight alone, with considering the polydispersity index, may mislead you in defining the polymer. Now, that is true in the fact that only with number average you cannot define the entire distribution. You will need the weight average also, since the entire broadness is defined by that. So you can calculate the mass average, sorry, weight average from that, as you can multiply the number average with the polyviscosity index, and we will arrive at the weight average. So the second and third options are the right ones. Sorry, the first, second, and third options are the right ones. Next one we have, what are the other classifications of suspension polymerization? Now, what happens in suspension polymerization, as the name suggests, we are creating a suspension of the formed polymer. Now, how do we do that? Is we mechanically produce agitation, either through impeller or any kind of mixer, which will mix the monomers, usually in the liquid phase. Why we are using the liquid phase? Because it increases the handleability of the polymer since they are so viscous. And since the polymerization process itself releases a lot of heat, it is very easy to dissipate that heat using the liquid medium. And once the polymerization starts, the polymers are formed inside the suspension itself and they are suspended in the liquid medium. Now, when these polymers are formed, if these polymers are soluble in their own monomers, if some example leftover monomers are there inside the solution itself, which obviously are because the once the equilibrium constant for a reaction is reached, no more reaction will occur. So the final form polymer, if it is soluble in its own monomer, it will dissolve in that and it will form a bead, smooth bead. And that smooth bead is why the name bead polymerization comes for the suspension polymerization. Now, if the polymer which is formed is not soluble in its own monomer, it won't form the bead and it will separate out and it will be present as a powder. And that gives the name powder polymerization. So bead and powder polymerization are the classifications of the suspension polymerization. Emulsion polymerization is altogether different. What happens in emulsion polymerization is that the emulsification process is there and you have to add a surfactant in. Emulsion polymerization is entirely separate. So that is not the correct answer for this question. Next one we have is, which one of the following properties of the polymer is desirable during the synthesis of polymer? So, for example, if you are synthesizing it, what are the properties which are desired? So, first of all, lower molecular weight will not be desired because you want the polymer to polymerize as much, right? You want the monomers to polymerize as much, which means that you will need a higher molecular weight. So, you're always expecting to obtain a higher molecular weight, or whatever your application needs, you want something to uh, stand on that. So that's why we need the specific polymer molecular weight to that one. So that is not desirable. Lower molecular weight is not desirable. Second one is impurities. Now, we definitely don't want impurities in our polymers because presence of impurities will first of all hinder the polymerization reaction in itself and it will create unnecessary byproducts, or uh, it will create quite problems in the handling of the polymer itself. So that is again undesirable. Third one is the low viscosity. Low viscosity is desirable during the synthesis of polymers because handling such high viscosity polymers is very difficult, and that in itself is a challenge. That's the exact reason why low viscosity is what is desired. So, third one is the correct answer. Next, we have completely amorphous polymers showed only Tg, glass transition temperature, plus crystalline polymers showed Tm, and semi-crystalline polymers exhibit both temperatures. Now, first and foremost, you need to know is that all polymers are semi-crystalline in nature. Why? Because all polymers will definitely have some crystalline features and some amorphous features. Now, what is the definition of amorphous and crystalline polymers? Then is that it depends on the crystalline percentage or the amorphous percentage present inside it. For example, if you have a spectrum of 100, and if your polymer is 90% crystalline and 10% amorphous, you can call it a crystal polymer. And if it's 90% amorphous and 10% crystalline, you can call it amorphous polymer. So that's how the definitions are made. But polymers are semi-crystalline in nature, and that is exactly how their flexibility and moldability comes from. That is why the definitions are made in such way. So amorphous polymers, what happens is that Even though the polymer chains are present in a haphazard manner, as we all know by definition, what is amorphous and what is crystalline. Since they're present in a haphazard manner, they will definitely have some structure at their respective temperature. If you increase the temperature, they will come to a position where these haphazard chains are free to move, and that exactly is glass transition temperature. They only, amorphous polymers only show Tg because the chains are already not arranged in proper fashion, and their secondary forces, which are involved in close packing of the polymer chains, are not active at all. So if you increase the temperature, they will start flowing readily, and you will have a Tg in itself. Then we have the crystalline polymer. What happens in crystalline polymer is that your polymer chains are already arranged in a close packing manner in a uniform way. They are already present like that. What's going to happen in that is that uh, as you increase the temperature, these chains will not have sufficient energy to break the secondary forces of the close packing which has been arranged for them. And as you keep increasing the temperature, a point will come where all molecules will suddenly have enough energy to move around. And that is exactly the point where the melting happens. And since they are crystalline polymers, crystallization heat won't be achieved, which you can see right here on the right hand side graph. We have a differential scanning calorimetry graph right here where we have the heat flow and we have the temperature. Now, this heat flow can either be expressed as endothermic or exothermic. So the position of the peaks will change with respect to that. So you can see right here that the first dip right there is the glass transition temperature. Then we have the crystallization temperature. This temperature is the temperature where your chains are arranged in a particular manner to form the polymer crystals. And this is the temperature where your crystallinity of the polymer in itself is defined. Now, how is it defined is once you reach this temperature from the melting point, which comes later after the crystallization one, once the polymer is molten, all your chains are free to move. If you cool those chains down slowly, they will have sufficient time to form the crystals. If the polymer is cooled down suddenly, the polymer chains will not have enough time to arrange themselves into a proper orderly fashion. And then what will happen is they will form a amorphous zone inside the polymer, and that will give you the amorphous polymer in itself. That's why that zone is very important. So you have this. And on the left hand side, you can see how the property of the polymer changes with respect to temperature. When we are at the lower range of the temperature, the polymer is present in its glassy state. And as you are increasing the temperature, you see the transition zone, and then we get to the rubbery state where the polymer becomes extremely flexible and then starts flowing, starts stretching around, and then the viscous flow is initiated as the temperature increases. Basically, your polymer has already molten in. Okay, so moving on to the next question, we have
So just one doubt.
yeah,
As the previous question, as you were speaking,
yeah.
will the semi-crystalline material will have a specific melting point, or else it would have a range? I'm not sure about it actually.
Polymers definitely have a range of melting point because as we know that polymers are made up of different chains. Okay, so these chains will definitely have different kind of packing structure inside the polymer molecule, and at different temperature, like in that close range in itself, will start moving up. So definitely the melting point is not exactly a sharp melting point, but it's rather more of an average, which means that as you are approaching close to that melting point, the polymer will already start flowing. You can see that. And at that temperature, it's definitely melting. Okay.
Okay, so if we are trying to increase the crystallinity of a polymer by
Yeah.
any process by annealing also, so
Yeah.
we can narrow down the melting range into. We can just narrow down now. We can reduce the range into a specific point. Can we do it actually?
But reducing the range of the melting point of the polymer is actually quite difficult. Why? Because you will need to increase the crystallinity to quite a bit. You will need to make the polymer in such a way that it will only have sufficient energy for the molecules to move around at that particular temperature. You can like crystallize it repeated cycles. You can do that for a thermoplastic polymer, but I'm not sure it will work because the molecules themselves will have that kind of tendency to move around at that particular temperature or that range.
Okay.
So that's why, yeah.
Okay.
Okay. Yeah. Next one we have, which of the following statement is correct for the order of the reaction? First question is the overall order of the reaction can be a fractional or a whole number. So from the classic definitions of the reaction kinetics, we know that reaction orders can be fractional or whole numbers. That is true. Second one we have is the sum of the power raised to the concentration terms in the rate law is said to be the order of reaction. This is also true. We know that this is the definition of the order of a reaction, that the stoichiometric coefficients of the concentration terms to which they are raised is exactly the definition of the order of the reaction. Then it can be defined for elementary and non-elementary reaction systems. This is also true that because if the reaction is occurring in a single step, you can define the order of the reaction for that particular step. Or if it is happening in multiple steps, you can define the order of reaction for the multiple reactions which are occurring in the series of that single reaction. And from there, you can justify the entire thing for the non-elementary reaction. Then the fourth one we have is the order of reaction and molecularity are always same for a reaction system. Now this is not true because the molecularity or the idea that the reaction occurs when molecules are colliding together, that for that definition, the molecules which are participating in the reaction in itself will may not match the order of the reaction. So that is not always true. So that's why the order of the reaction and molecularity may not always be true. And that is the incorrect statement of the for this question. So the fourth one is the incorrect one. So yes, if you have like I've already explained all of them. So if you have any doubts or anything else from the course material, you can ask me. I will try my
So,
best to clear
so
them.
can you please explain just the first question? I was not hearing it properly. Just the first question.
Oh, okay, okay. I'll explain. Yeah. So the first question is the which one of these is correct? Which numbers? These are the dimensionless numbers. So which dimensionless numbers definition is correct? So I have put all the definitions for the respective dimensionless numbers which have been asked in the question. So first one we have is the Biot number, where the definition, the option says convection from the surface to the conduction through the body. So you can imagine this as take a hot solid steel sphere, and dip it inside a liquid, water, for example. What is going to happen? Heat is going to travel from inside the center of the sphere to the surface of the sphere, and then from there it will be convected out into the water. So what's going to happen is the heat has to travel through the entire conduction zone inside the sphere. Okay, so that is the conduction through the body, and then it will go out through convection. That is convection from the surface. So the definition right here says that conductive resistance inside the solid. Now in the numerator it's saying resistance in the solid, which means that the conduction will be the reciprocal of it. And in the definition also, you have the conduction through the body in the denominator part. And then we have the convective resistance in thermal boundary layer. Thermal boundary layer is formed where the liquid and the sphere surface are there. So then we have the thermal boundary layer being formed there. So the convection will occur at that place. Okay. So that's why again it's saying convective resistance. So again reciprocal will have to take, and the convection term will come to the top in the numerator. So that's how the Biot numbers definition is convection from the surface divided by convection through the body. So it's correct. Second one we
So,
have the
so the first one is correct. Even if the values are reversed, even though it
yeah
is correct.
yeah it is correct. Because the correct definition is exactly that convection from surface divided by the conduction through the body. Okay.
Okay, sir. Okay, sir.
Hmm. Then next we have uh, the Brinkman number. In Brinkman number we have the viscous heating divided by the conduction heating. So what's happening here is you can see the definition again for the Brinkman number. We have mu u square divided by KTW minus T. So We have the ratio between the heat produced by viscous dissipation and heat transported by the molecular conduction. Molecular conduction, that is the temperature difference multiplied by the K, thermal diffusivity. You can see right here, thermal, sorry, heat, the coefficient right here, you can see that K, and we have the Tw minus T naught, that is the temperature difference. And mu used here is the viscous dissipation. Viscous dissipation occurs whenever you have an extremely viscous fluid, and when the layers of that viscous fluid rub upon each other, you will have heat produced. And that heat which is produced when it is dissipated, that is exactly basically what is called the viscous dissipation, viscous heating. And this viscous heating will produce that the heat is dissipated through the viscosity is basically that is termed as the viscous dissipation. Okay, and uh, then we have the definition for the Brinman number. Again, we can see that viscous heating by conduction, and that matches the standard definition right here. Next, we have the Dam-Polar number. Dam-Polar number is present right here. You can see KL square divided by D. Okay, so we have K, that is the rate constant, and then in the denominator we have the diffusivity. Okay, so in the option, the definition has been written as reaction energy by the internal energy. Now, in the Dam-Kohler numbers definition, we have KL square by D. So K is your rate constant, and you can synonymously use that for the reaction energy term. So that is equal to that divided by the internal energy. Now that can be used for the term diffusivity. Why? Because the internal energy of the molecule or the concentration differences which cause the diffusivity to occur can be used as a term for the internal energy, and that's how it is defined. So dipolar number's definition will be reaction energy by the internal energy. But the fourth one we have is the surface tension stresses by deviation stresses for the capillary number. Now, the definition of capillary number is ratio of viscous force to the surface tension force. This is useful in the places where there is an interface formed between the liquids, or the liquid is at a surface where the viscous force and the surface tension forces are acting together. So, in that case, the ratio of viscous force to surface tension force is the definition. But in here, we have the definition as surface tension stresses to the deviation stresses, which is incorrect. So that's why you need to this option is incorrect. The first three are the right one. Okay,
Okay, sir.
yeah, that's it. Okay, then today's class is over. If you have any other doubts from your uh, lecture or anything, you can ask me. You can write down the doubt in the chat box, and maybe I'll try to clear it. If I can't, I'll clear it in the next.